Hi everyone, this is Tanya Chiu. In this video, I am going to discuss Cambridge International AS Physics Paper 2 Structure Questions, May June 2025, Paper 23. Are you ready? Let's dive into the question number 1. Now, question number 1. A, define velocity. Velocity is being defined as rate of change of displacement. Remember, velocity is a vector quantity. Displacement is also a vector quantity. B, in an experiment, two objects A and B are released from the side of a building as shown in Fig 1.1. Object A is released from rest, so you better write it down to avoid careless mistake just in case. At a height of 10 meter above horizontal ground, object B is released with an initial outward velocity of 3 meter per second at a height h above the ground. Both objects take the same time to reach the ground and they do not collide with each other. Air resistance is negligible. Calculate h. Now I am going to use, because there's no, okay, so since I'm supposed to calculate h, right, okay, h is related to B for object B. I am going to use one of the kinematics equation, which S equals ut plus half gt squared. And I'm going to consider upwards direction as positive direction. So now S, right? Okay, S is the displacement. So B is going upward. So I need to get this part of the displacement because B is going upward. So going up with this displacement. This displacement is 10 minus H. So B is going upwards with 10 minus H. Let me write it nicely for you. 10 minus h going upwards, and then after that reaches the maximum height and going downwards and reaches the ground at 10 meter. So the displacement would be 10 minus h first, outwards direction, and minus 10. Why minus 10? Because after that the displacement is going downwards. B is going downwards, so the displacement has to take a negative value. So the initial velocity is 3. And I don't have the time. Plus half g is going downwards, 9.81, and t squared. Don't worry about t because t is a scalar quantity. I do not have the value of t. I have two unknowns here. So that is why I have no choice but to do for object A to find the t, to find the time. Right, because both objects take the same time to reach the ground. So I am still going to use the same kinematic equation as equal to ut plus half gt squared. But the good thing about A is that you can just ignore ut here because A starts from rest. So the displacement of A is negative 10 because A is going downwards, is equal to half negative 9.81 because G is always acting downwards, T squared. Negative and negative you can actually cancel, T squared or just T. Okay, I'm going to make T as a subject right away. So the T is equal to negative 10 times 2 divided by negative 9.81. So bear in mind, negative and negative, right? You just cancel them off. And the t that I got was 1.43 seconds. Sub into the equation of B. So 10 minus h minus 10. So I get negative h here. 3, 1.43 t plus 1 over 2, negative 9.81. 1.43, you square it. I got my negative h equals to negative 5.74 meter. Therefore, h is equal to 5.74 meter. So 5.74 meter is the answer. Now, see, in a second experiment, object B is released from the same height as in B, but with the same speed of 6 meters per second at an angle of 60 degrees to the vertical, as shown in Fig 1.2. Now, first part, state and explain whether the time taken for object B to reach the ground is less than, same, or greater than the time taken for the first experiment. So since this speed is deviated through 60 degrees from vertical, I need to find my vertical velocity, initial velocity of B, right? Initial velocity of B, which is here. Now I continue. I draw a right angle triangle so that you can see it clearer. So this is my right angle triangle. I am going to find this velocity. This is called initial velocity. Initial velocity in vertical direction because the height is in vertical direction and g is in vertical direction. So you have to resolve your initial velocity into vertical direction. So this is adjacent cos 60 degrees is equal to u in vertical direction divided by 6. So u in vertical direction is 6 cos 60. And I got 3 meter per second, which is lesser. Right, since the speed is the same, right, oh, the initial velocity is the same because the initial velocity is 3, even though they projected out the object B at a certain angle due to the angle. Right? When you resolve it into vertical direction, you got the same value as the initial speed, which is projected in vertical direction. So I would say the time reaching, okay, the ground would be the same because it is the same initial vertical velocity is being released. I would say time taken for object B to reach the ground is the same as first experiment. Time taken for the first experiment. So explanation. Why? Because as initial vertical. You have to resolve to vertical because G is acting in vertical direction. Initial vertical velocity of B is 3 meter per second, which is, okay, which is the same. Initial vertical, initial vertical velocity as the first experiment, which is the same, which is the same as initial vertical velocity in the first experiment. Done. Second part, by considering energy, state and explain whether the speed at which object B reaches the ground is less than, same, or greater in the first experiment. So you compare with the first experiment. So since the speed projected is larger, so I would say the initial kinetic energy, right, of the initial kinetic energy, initial kinetic energy of object B is greater. So due to the initial kinetic energy projected, okay, is greater, that is why the total initial energy of object B is greater. Why greater? Because the initial energy, total initial energy of B is gravitational potential energy, but it is projected, right, at the same height. So gravitational potential energy is the same. It is just that kinetic energy because it is projected at higher speed. Speed, you ignore direction. So since it is projected at the higher speed, that is why the initial kinetic energy of object B is greater. So, okay, since they asked us to consider about the energy, I would say the change in gravitational potential energy of B is the same, basically the same as the first experiment, but the change in kinetic energy is greater since, okay, the initial speed is greater. Done. Number 2A, define moment of a force about a pivot. What is moment? Moment is being defined as product of force and perpendicular distance from pivot. That's the definition of moment of a force. B, three objects, A, B, and C, are placed on a horizontal beam. The beam is in equilibrium. Okay, this beam is in equilibrium as shown in Fig 2.1. The beam is uniform. Uniform means that the center of gravity of the beam must be acting at the center point, okay, the center length of the beam. Since the length of the beam is 9.0 meter, center of gravity or the weight in which the point where the weight is acting would act at 4.5 meter from both ends. The pivot is at the midpoint, so the pivot is acting at the center of gravity of that beam. So you can ignore the weight of the beam. Object A has a mass of 90 kilogram and is at one end of the beam. Object B has a mass of m and is a distance 3 meter from the pivot. Object C has a mass of 150 kilogram and is at this other end of the beam. Calculate m. So since, okay, it is in equilibrium and the pivot is being given, so you have to use the principle of moment. Do you still remember what is principle of moment? Principle of moment states that for an object or a system to be in equilibrium, the total clockwise moment must be equal to the total anti-clockwise moment. So now at the center of gravity of A, this is where the weight of A is acting. So weight of A is equal to mass of A, 90, times 9.81. So I got 882.9 Newton for A. Don't bother about the significant figures or the decimal point that I put because this is not my final answer just yet. Right? Weight of B will be mass, m, mass of B is m times 9.81. And the weight of C, center of C is here. This is weight of C, which is equal to 150 times 9.81. So it is 1,471.5 Newton. Now, since we are done with that, I would like to identify whether these forces are producing clockwise or anti-clockwise moment. Pivot is here. So look at A. Weight of A is going downwards. While going downwards, it will have to turn towards the pivot. This is a direction of turning. This is called anti-clockwise direction. B going downwards as well. While going downwards, it will turn towards the pivot. This is also in anti-clockwise direction. C going downwards, while going downwards, it will turn towards the pivot. This is called clockwise direction. Since I have already identified the clockwise and anti-clockwise direction produced by all these three forces, I can safely use my principle of moment. Principle of moment states that the total anti-clockwise moment must be equal to the total clockwise moment. Anti-clockwise moment, I start with A first, the weight of A or the force. Gravitational force of A times the perpendicular distance between A and pivot. Since the object A is placed at one end, remember the beam is uniform, so the distance between one end to the pivot is 4.5 meter. How do I get 4.5 meter again? I take 9 divided by 2. So 4.5 meter plus, okay, weight of BM times 9.81 times perpendicular distance from the pivot, which is 3. And then clockwise moment produced by the weight of C, 1,471.5 times 4.5. Why again 4.5? Because C is placed at the other end. Now, okay, work it out. 82.9 times 4.5. My answer is 3.1 plus 29.4 m equals 6621.8. Then to find my n, work it out. 6621.8 minus 3973.1 divided by 29.4, and you're supposed to get 90 kilogram. So the mass of B is 90 kilogram. Now, the second part, object A is removed and replaced by a wire fixed to the end of the beam and to the ground, as shown in Fig 2.2. After the change, the beam is again horizontal and in equilibrium. The positions of B and C are unchanged, so I better write it down. Okay, weight of B is equal to mass of B times 9.81, get a value later. And then perpendicular distance between B and the pivot is still the same, which is 3 meters. And C, the weight of C is equal to 1471.5 Newton, and the perpendicular distance between C and the pivot is 4.5 meters. And it is in equilibrium. Remember, the positions of B and C are unchanged. The wire has a diameter of 1.8 times 10 to the power negative 3 and has a strain of 1.2 times 10 to the power negative 3. The wire is not extended beyond its limit of proportionality. So that means the wire obeys Hooke's law. Calculate the Young modulus of the wire. So do you should remember Young modulus is being defined as stress divided by strain. Stress and strain are not, or strain is given, but the stress is not being given. Stress is equal to force of the wire divided by cross-sectional area of the wire. So if you want to find the cross-sectional area of the wire, you have to remember A is equal to pi r squared, because the wire is, the cross-sectional area is circular. So, but the problem is the question does not provide us with radius. R means radius. It gives us diameter. So you know that R is equal to diameter over 2. A is equal to pi, the bracket, diameter over 2, you square it. Therefore, your A is pi d squared over 4. Remember that. Now I find the cross-sectional area first. How about that? Make the calculation simpler. Pi diameter is 1.8 times 10 to the power negative 3. You have to square it, divided by 4. Okay, when you divide by 4, your answer should be, let me do a little bit of calculation, times 10 to the power negative 3, and then you have to square it, and times pi, which is equal to 2.54 times 10 to the power negative 6. So I got the value, meter square. But the problem here, I have another problem here. Never mind, I write down y, Young modulus, is equal to f of the wire divided by area. So area is 2.54 times 10 to the power negative 6. And then divided by 1 over strain, divided by strain. So times 1 over strain, which is 1.2 times 10 to the power negative 3. Now I don't have the force from the wire. I need to find the force from the wire first in order for me to get the value of Young modulus. But I try to simplify here. Force of the wire over 2.54 times 10 to the power negative 6 times 1.2 times 10 to the power negative 3. Here I got 3.05 times 10 to the power negative 9. I leave it first. So I'm going to use the principle of moment because the beam is in horizontal. This is the force on the wire. Force on the wire. Again, repeat the same process like what I did in the first part. So I'm going to determine whether this force of the wire is providing clockwise or anti-clockwise moment. So force of the wire is acting downwards. While going down, it will seek for the pivot, which is on its right-hand side. So it will have to turn towards the right-hand side. This is called anti-clockwise direction. Weight of B turns towards the pivot. This is also called anti-clockwise. Weight of C turn towards the pivot. This is clockwise direction. Since I have already identified my clockwise and anti-clockwise direction, I can safely use the principle of moment. Total anti-clockwise moment equals total clockwise moment. Total anti-clockwise moment is the force from the wire multiplied by perpendicular distance from the pivot, because the wire is at the other end. So it is 4.5 meter plus the weight of B. Weight of B is 90 times 9.81 multiplied by perpendicular distance, which is 3 meter, equals to weight of C. Weight of C is 1471.5 times the perpendicular distance from the pivot, which is 4.5. And you work it out, you are supposed to get the force of the wire, which is equal to 883 Newton. Since I got that, I just replace that. 883 divided by 3.09 times 10 to the power negative 9. So let me do it. So this, 3.05, sorry, not 3.09, yeah, 3.05. 05. So 883 divided by 3.05 times 10 to the power negative 9. You are supposed to get 2.89, right? Or 2.9. So I get 2.9 times 10 to the power of 11 Pascal. So 2.9 times 10 to the power 11 Pascal is our answer. Now the second part, object B is now moved to a new position closer to the pivot without passing it. Oh, that means object B is here. Okay, I'm going to draw it. So let's say closer towards the pivot. Can you see? When B is moving closer towards the pivot, the perpendicular distance of B is decreasing. So the anti-clockwise moment produced by B is also decreasing. Right, but the beam is again horizontal. That means it has something to do with the wire. So I would say that since we have to still apply the principle of moment, since the beam is again horizontal and equilibrium, that is why, okay, the strain, what happened to the strain of the wire? I want you to see this. Okay, I would say that the force, okay, by, okay, wire or force on wire must be increasing, because to produce a larger anti-clockwise moment, since the anti-clockwise moment produced, okay, by B is lesser, on wire increases. So let me write it down. It increases. Okay, and the Young modulus is constant. Young modulus for every wire, there's only one Young modulus, right? Cannot be two. Is constant because we are using the same type of wire. So I want you to see this. Y is equal to F over A times 1 over strain. So since this is constant, force is increasing, strain must be decreasing to balance the value of the Young modulus. So that is why I would say that strain in wire decreases. Done. Number 3, a car of mass 1,500 kilogram is traveling along a straight horizontal road at constant velocity. Okay, constant velocity is the keyword, meaning to say that the resultant force acting on the car is equal to 0. Forward force is balanced by the backward force. The car is subjected to total resistive force F as shown in Fig 3.1. A show that the power developed by the engine in overcoming the total resistive force is given by the equation. Now, power, I am not going to explain the symbol because the question has already explained, is being defined as work done per time taken. Work done, okay, so I am going to put symbol here. Erase first. P is equal to W over T. And W is equal to force times distance. Move in the direction of force. Right, so I am going to get this. Force times distance, move in the direction of force divided by time. And I want you to see this. Since the speed of the car is constant, you can safely use V is equal to distance over time. This is only valid. You can only use this when the speed of the car is constant. So I'm going to sub it in. P equal to FV. Ta-da! Proven. Now, B, the car now moves up a slope at a constant speed of 30 meter per second. The slope is at an angle to the horizontal of 6 degrees, as shown in Fig 3.2. The total resistive force acting on the car is 1,600 Newton. Show that the increase in the gravitational potential energy of the car in a time of 1 second is 46,000. Still going to use this because the speed is constant, Fv. The problem is with the F. I want you to see this. The car is going up an inclined plane, and the gravitational potential energy is acting vertically downwards. So this is the center of gravity of the car. Okay, what you need to do, you draw a normal towards the center of gravity of the car. So I get my ruler first, draw normal to the inclined plane, yeah? Normal, that means 90 degrees to the inclined plane, something like this. Okay, roughly normal. I'm going to use red color. So this is the normal passing through the center of gravity. Okay, and then, okay, I want you to remember that weight is acting vertically downwards. So this is where the weight of the car is acting. So keep my ruler first, I'll show you. This is where the weight of the car, weight of car is acting. So when you do this, okay, this is 90 degrees. I need to find this value. This is the, okay, this value is almost, okay, parallel. Okay, this value must be parallel to this inclined plane. Something like this. Okay, center of gravity. Okay, this is where the weight is acting. And then this is, okay, we are supposed to find, I draw it larger for you to see. This is where the weight is acting, center of gravity of the car, and then this is the incline. I just want to draw almost similar incline. Okay, wait. Okay, like this. This is the incline. Okay, where the car is moving up. This is called component of weight. Okay, of car moving up incline. So this is 6 degrees. So this is 60 degree. Can you see that the angle is quite small? So how do I find the value there? This is called weight of the car. Weight multiplies by sine 60, opposite over hypotenuse. Right, I'm going to use that. So the force would be mg, or the weight of the car. Weight is mg sine 6 degree times the constant speed. So the mass of the car is 1,500, the g is 9.81, and then you multiplies by sine 6 degree and multiplies by 30 meter per second, not 30 degrees, 30 meter per second. And you shall get the answer of power as, wow, that's a lot, okay? 46144.09 watt. Don't worry, that's not the end of the answer. That's not my final answer. Energy is equal to power times time. So power 46144.09 times 1 second. So my energy is 46144.09 joules, and I round it off to 46000 joules. That's the answer. Use the second part. Use the information in B part 1 to determine the power developed by the engine to move the car up the slope. So the power developed by the engine has to be resultant force. Total resultant force acting on the car times V. Total resultant force you have to add because the car is still moving with a constant velocity, okay? And the component of weight going down the slope is acting in the same direction as the resistive force. That is why the resultant force, you just take resistive forces plus mg. Okay, 1500 times 9.81 sine 6 degree, and all these multiplies by 30. And the answer is 9.41 times 10 to the power of 4 watt. 9.41 times 10 to the power of 4 watt. C, the car picks up a passenger and then continues up the slope at the same speed as in B. State and explain the effect, if any, that the passenger has on the first one, air resistance acting on the car. Since the speed of the car is constant, okay, since the speed is the same as in B, air resistance remains the same. Because air resistance depends on speed. Speed increases, air resistance will increase. But if the speed is constant, air resistance will still be the same. Right, the power developed by the engine. Could you see that one passenger, right, it will add it to the overall mass of the car. So since the mass of the car is increasing, the total mass, right, will be increasing. That is why, right, resultant force will be increasing, which increases the power. So I will say the total mass increases, okay, which causes resultant force to increase, hence power increases. Power developed by the engine will also increase. The next one, question number 4. State the principle of conservation of momentum. So the principle of conservation of momentum states that in a closed system or isolated system, you have to put in. Why? Okay, maybe some of you wonder, what is closed system? What is isolated system? Isolated system or closed system. Before I explain that, okay, back to the definition of momentum. Momentum is being defined as mass times velocity. As long as object has mass and object is moving, object has momentum. Do you agree? So whenever we move, we experience, let's say, talking about me, whenever I move, I will experience resistive forces like maybe air resistance, like maybe frictional force acting on me, right? So when I say a closed system, meaning to say that when I use the principle of conservation of momentum, I ignore all the resistive forces that could act on the moving object. That is why it is a need you put a closed system. Yeah, in a closed system, the total initial momentum before collision must be equal to total final momentum after collision. That's the principle of conservation of momentum. B, an object A of mass 4 kg travels at a speed of 6 meters per second to the right on a horizontal frictionless surface. It moves towards the second object B of mass 2 kg that is moving at a velocity of 3 meters per second in the same direction as A. Same direction, right? That is a good news. As shown in Fig 4.1, object A collides with object B and the two objects joins, okay? See, this is before, I'll draw after. A and B will join together, move with the same final velocity. Calculate the final velocity V, right? This is called inelastic collision. So I'm going to write total momentum before the collision must be equal to the total momentum after the collision. Total momentum before, remember momentum is a vector quantity. This is U1, object 1. This is U2, object 2, right? This is M1. I put this as M1. I put this as M2, M1, M2. And then this is a final, okay? Velocity. Since the two objects are moving in the same direction, you put positive to all the velocities. Right. Now, total momentum before M1 U1 plus M2 U2 is equal to total mass because they join together. Total mass of the two objects times their final velocity. M1 U1, M1 is 4 kg moving with 6 meters per second plus M2, 2 kg moving with the initial velocity of 3. Okay, not 2, but 3. 3 meter per second is equal to the total mass 4 plus 2 times the final velocity. 24 plus 6 is equal to 6v. Hence, v is equal to 5.0 meter per second. So the answer is 5.0 meter per second. Second part, the percentage of the total kinetic energy of the two objects that is transferred to the other forms of energy during the collision. You need to know that this is inelastic collision. If we are talking about inelastic collision, the total kinetic energy must always be lesser. Right, okay. Now I am going to find the total initial kinetic energy. Initial is equal to the kinetic energy of object 1, m1, 4, times the initial velocity of object 1, 6 square, plus kinetic energy of object 2, which is mass is 2 kilograms, speed is 3, but you have to square it. So the total initial kinetic energy is 81 joules, and then the total final kinetic energy is equal to half the total mass of the two objects times their final velocity. 5 square, final speed, final velocity, you shall get 75 joules. So I calculate the change in kinetic energy or the loss in kinetic energy, 81 joules minus 75 joules, and I got 6 joules. Therefore, the percentage, right, of the total kinetic energy that is being transformed into other form of energy is equal to change in kinetic energy divided by total initial kinetic energy times 100%. So this is 6 over 81 times 100%. You should get 7.4%. 7.4% is the answer. Now, number 5A, state why sound waves cannot be polarized. You definitely know that that is one of the process or experiment which we can differentiate between transverse wave and longitudinal wave. Sound wave is the longitudinal wave. Sound wave cannot be polarized. Do you know why? Because the direction of vibration of the particles in sound wave occur parallel to the direction of propagation of the wave. Or in other words, I would say that the vibration of particles in sound wave, right? Sound waves occur in the same plane. Same plane, that means horizontal plane, or vibration and direction of propagation occur in the horizontal direction or occur in the vertical direction. Same plane as propagation of energy of the wave, of the waves. Right. Now, B, a plane polarized light wave is incident on the polarizing filter, as shown in Fig 5.1. The intensity of the light incident on the filter is I naught. The light is incident normally on the filter, and the transmission axis of the filter is initially perpendicular. Right, not parallel, perpendicular to the plane of polarization of the light. So it is acting perpendicular because, okay, the intensity of the light occur in a horizontal direction, let's say, and then this filter is perpendicular. Right, can you see 90 degrees, 90 degrees. So the filter now is rotated, okay, initially at 90 degrees. You start at 90 degrees. And then you rotate 360 about the direction of travel of the light wave. On Fig 5.2, sketch the variation of the intensity I of the transmitted light with the angle of rotation alpha, right, as the filter is rotated through 360 degrees from its initial position. So initial position is already 90 degrees. So when the initial position is 90 degrees, I is equal to I naught cos square 90. Initially is at 90. So when you cos, okay, initially at 90, because you don't be confused. they have already explained, question has already explained that this filter is placed at 90 degrees. Initially, we supposed to start at 0 degrees, but the question stated that this filter is 90 degrees, which is perpendicular to the direction of travel of the wave. That is why when you cos 90, you get 0. So, okay, and then, okay, rotate another 90 degrees. When you rotate another 90 degrees, that means the total rotation, already 90, you plus 90, you get cos 180. Cos 180 is, okay, I know, cos square 180 degrees. Right, and then cos 180 degrees, you add 90, becomes cos, okay, 270. Cos square 270, you get 0. Cos, okay, square 270, you add 90, becomes cos square 360, that gives you 1. And then cos 360 degrees, right? 360, you add 90, you get cos 450, so you get 0 right here. So your graph's supposed to be like this. Uh, like, okay, I'm so sorry. Okay, sketching skill is not so good. Okay, like this. Right, that's the answer. Now, second part, the amplitude of the incident wave is A naught and the intensity of the wave is I naught. Use Malus law to determine in terms of A naught the amplitude of the transmitted wave when alpha is equal to 20 degrees. Right, rotation. Alpha is the transmitted light with the angle of rotation. Right. Still remember Malus law? I is equal to I naught cos square theta. Theta is always measured from the line of propagation, right? Of the perpendicular line, right? Since alpha is 20 degrees, right? The theta has to be 90 minus 20. So it is 70 degrees. I is equal, and you know the, okay, relationship between I and amplitude, right? I is equal to amplitude square. So I have I is equal to a constant times amplitude square. So I'm going to stop in this equation. K amplitude square is equal to K A naught square cos square 70 degrees. K and K cancel, right? Square root A naught square cos square 70. So you get A is equal to A naught cos 70. So the answer is 0.342 A naught. 0.342 A naught is the answer. The next one, question number 6, what is meant by diffraction? Diffraction means spreading. You have to include this word because this is the key word. Spreading of wave when a wave passes through an aperture or a barrier or a gap. B, light of wavelength 720 nanometer is in a vacuum and is incident normally on a diffraction grating as shown in Fig 6.1. A screen is parallel to the grating, an interference pattern is seen on the screen, and the angle between the second order maxima is 52 degrees. Calculate the frequency of the light. Do you still remember the wave speed? V equals to F lambda. Right, how do I get the value of V? Because the light is traveling in vacuum. When the light travels in vacuum, the speed of light is 3 times 10 to the power of 8 equals to frequency. The wavelength is given as 720 but nanometer. Nano is one of the prefixes, which is 10 to the power negative 9 meter. So frequency is equal to 3 times 10 to the power 8 divided by 720 times 10 to the power negative 9. Frequency is given as 4.2 times 10 to the power of 14. 4.2 times 10 to the power of 14 is the answer. Now, second part, calculate the number of lines per unit length in the diffraction grating. So I want you to see this. This is a second order maxima. Second order maxima, the angle is being measured from the second order to the next second order. You have to remember when we use the equation of the diffraction grating, d psi theta n is equal to n lambda psi theta. Psi that theta has to be based on the horizontal reference line or undeviated beam. So you have to draw this undeviated beam or zero order. So I'm going to draw that up. Okay, give me a while. Make sure that my ruler is horizontal first. Okay. I'm going to draw the undeviated beam. So this is called undeviated beam or zero order. So your theta has to be based on this. So this is called undeviated beam. Undeviated beam is the brightest beam. So your theta, can you see that? This is called your theta. Theta has to be equal to 52 divided by 2, which is 26 degrees. And after that, you can safely use this equation. So I'm going to modify this a bit. This is called grating spacing. Grating spacing has a relationship, okay, with number of lines per meter. So I'm going to sub it in. Sine 26 is equal to 2 lambda. Lambda is 720 times 10 to the power negative 9. So I got the value of 1 over n, which is equal to 3.28. 1 over n is d, times 10 to the power negative 6. Therefore, n is equal to 3.04 times 10 to the power of 5 per meter. This is in meter. So 3.04 times 10 to the power negative 5 per meter, because this is number of lines per length. Length is measured in meter. Second part, the light in Fig 6.1 is now replaced with light of a different wavelength, lambda. It is observed that the third order maxima of this light are at the same positions as the second order maxima of the light in Fig 6.1. Calculate in nanometer the wavelength lambda. So since this is third order, so I'm going to use this. D psi theta 3 is equal to 3 lambda. D is still the same. Grating spacing is still the same because we are using the same, the grating. We are using the same, same diffraction grating, right? So we are still using the same thing. So that is why I'm going to replace this with the value that I got just now, 3.28 times 10 to the power negative 6. Sine, they mentioned that the angle is the same, right? Same position as the second maxima. So the angle will be the same, 26, which is equal to 3 lambda. Lambda is equal to 3.28, sorry, 3.28. 3.28 times 10 to the power negative 6 sine 26. Remember to change your calculator to degree instead of radian, divided by 3. Lambda is equal to 4.79 times 10 to the power negative 7 meter. But you have to put it in terms of nanometer. So nanometer is equal to shift 789. So 479 nanometer. 479 nanometer is the answer. The next one, question number 7, a nichrome resistant wire has a length of 150 cm, cross-sectional area of 2.45 times 10 to the power negative 7 meters square, and resistivity of 1.12 times 10 to the power negative 6 ohm meter. Calculate to 3 significant figures. 3, the resistance of the wire. So I would say resistance is resistivity times length divided by cross-sectional area. So resistivity is 1.12 times 10 to the power negative 6. Length is 150 cm. You have to convert to meter. So this is 150 divided by 100. So you shall get 1.5 meter. Make sure that this is in meter, and area is already in meter square. So you can just leave it. And your resistance in 3 significant figures. Let me do it. 1.12 times 10 to the power negative 6 times 1.5 divided by 2.45 times 10 to the power negative 7 And I got 6.86. 6.86 ohm. 6.86 ohm is the answer. Now B, the nickel wire forms part of the potentiometer circuit together with a cell of electromotive force 1.2 volt and negligible internal resistance as shown in Fig 7.1. The circuit is used to determine the EMF of cell X. The galvanometer is used in the null method to find the null point 64 cm from the left-hand end of the nickel wire. First part, explain what is meant by null method. Null method means that the galvanometer will read zero. So why the galvanometer reads zero? It is because the EMF of the cell X is equal to the PD across the 64 cm of the nickel wire. So I would stick that. Galvanometer shows zero reading. And then when EMF of cell X equals to potential difference across 64 cm of nichrome wire. That's the answer. We move on to the next one. Calculate the EMF of cell X. Since this is a potentiometer, I'm going to use the potential divider concept. So potential divider concept that I'm going to use is V output over V input, or the total EMF, is equal to, I'm going to use length, output over total length. V output is actually the EMF of cell X divided by V input. How do you see V input, right? V input is the EMF of the driver cell. This is called driver cell. Okay, so put this as 1.2 volt. Length output is the length connected to cell X, which is 64 cm, and divided by the total length of the nichrome wire, 150 cm. So cm and cm can be cancelled, so I'm not going to change that cm to meter. Therefore, EMF of cell X is equals to 1.2 times 64 divided by 150, and I got 0.512 volt. 0.512 volt is my answer. The third part, the cell of EMF 1.2 volt is replaced by a new cell. With the same EMF, but with an internal resistance that is not negligible. State and explain the effect, if any, of the internal resistance of the new cell on the position of the null point. You could see that EMF is equal to the potential, the terminal PD, plus, okay, PD across the internal resistance. So the EMF now split between the two PDs. Therefore, since this due to this internal resistance, EMF value is the same, which is still 1.2, but it has to be shared. The terminal PD across cell X and across the wire need to be shared with the internal resistance. That is why the internal potential difference is decreasing. When the internal resistance is decreasing, or it causes the total resistance of the whole circuit is increasing, the length must be increased. The length output, right? So the internal resistance, I'm going to write this, internal resistance causes terminal potential difference across cell to decrease. And the total resistance increases, and therefore, okay, length position of the null point. Position of the null point. Okay. If you want to get it 0 again, so you shift the position because the total resistance increases, so you shift to the right hand side. So the null point position, null point position is shifted towards right side of nichrome wire. Okay, nichrome wire, nichrome. Okay, nichrome wire. Now, number 8A. An antiparticle equivalent of a neutron is called antineutron. The quarks in the antineutron are the antiparticles of the quarks in the neutron. Elementary charge is E. In table 8.1, state the flavor and charge of the three antiquarks that comprise the antineutron. First of all, I need to write neutron first. Consists of down, down, up quark. So the anti-neutron consists of anti-down, anti-down, and anti-up quark. So I'm going to write that anti-down first, or this, and then anti-down, the other one, which is down with a hat, and anti-up, okay, bar with a U. And down quark is equal to negative 1 over 3e. So anti-down opposite of it, it has to be plus 1 over 3e. So this is plus 1 over 3, this is plus 1 over 3e. Up quark is positive 2 over 3e. Therefore, anti-up is negative 2 over 3e. Negative 2 over 3e. Done. Now, B in a beta negative decay, a neutron decays to form a proton. Theory predicts that an anti-neutron should decay to form an anti-proton. A particle and an antiparticle should also be observed. State the names of the particle and the antiparticle. So I would say that when a neutron, anti-neutron, okay, neutron decay to form a proton first. Okay, 1p plus 0, negative 1 beta plus anti-neutrino. Right. And then now, okay, this is about anti-neutron. Neutron up, up, down, anti-neutron up. Neutron is down, down, up. Okay. Down, down, up. Anti-neutron supposed to be anti-down, anti-down, and anti-up. Proton is up, up, down. So anti-proton supposed to be anti-up, anti-up, and anti-down. So it is actually, okay, name the particle. The particle here, particle and antiparticles that present. So I would say that, oh, this is just a theory, okay? It's in beta decay, okay? So the beta decay, this is just a theory, so sorry. Okay, this is a decay of a neutron. So a neutron, it will produce a particle, which we call it as positron. Beta plus is called positron. An antiparticle to this positron is called electron. And that's a wrap for May June 2025, paper 23, right? Thank you very much for watching. If you think that this video is useful, just hit the like button, subscribe button, and I see you in the next one, right? Bye.